All right. Welcome everybody to today's IACS student seminar. I'm Tom Spratt, professor in linguistics and Logan Swanson's advisor. So Logan is currently a third year student in our PhD program. And over the course of last year, he started looking into the learning of syntactic structure, meaning sentence structure, which is a very, very hard and difficult problem that has occupied linguistics for decades. In my humble opinion, not much progress has happened on that front until recently when Logan started tackling that kind of thing. So in this talk, Logan is going to tell us more about syntactic learning over 3 years. Logan, take it away.
Okay, hi everyone, thank you for coming. Thank you so much, Thomas, for the introduction. Just so everyone knows, we're recording this session, and there are very sensitive mics in this room. So if you feel the need to comment to your neighbor during the talk, I won't personally be offended, but for posterity, they might be aware of whatever it is you said. So just so you know. Also, just, I don't know how this usually runs, but for my personal preference, if there's something that you're not following or need clarification on as I go, feel free to stick up a hand or interrupt me and get clarification like in the moment. Maybe like big picture questions we can save for the end, but yeah, don't hesitate to like try and get clarification so you can actually understand and follow the talk. Okay, so yeah, with that, let's dive right in. So today we're going to be talking about learning, and particularly the learning of syntax, which refers to sort of the structure of sentences. And so human language is kind of full of these patterns that might sort of seem arbitrary or pretty complex. Good. So let's take a look at this example here. This is an example from English, and anyone else who's a native English speaker, you might have this in your dialect. It certainly is true for my version of English, where you can say something like, you said that Mary saw John. That's totally fine. And you can also say it without the that. You can drop it. You said Mary saw John. Then if we want to make that into a question, we can either have the that or not. So you can say, who did you say that Mary saw? Or you can say, who did you say Mary saw? That's totally fine. But if we want to make it into a question, not about who was seen, but actually who was doing the seeing. So like we want to turn this Mary into sort of the thing we're asking about. Suddenly one of those options disappears. So it's okay to say, who did you say saw John? But it's not okay to say, who did you say that saw John? At least for me, that's pretty bad. I can't say that at all. Different English speakers might vary, but at least in my dialect, that's like pretty out. And that seems kind of unprincipled, right? Like that's sort of a strange pattern that we might not necessarily easily be able to see why that would be the case. And language is kind of full of these things, right? So if you think about, if you speak a different language natively, like your own native language or English or whatever else you speak, right? There's all these like weird patterns that, seem pretty complicated and maybe kind of, hard to figure out why they might be there, right? But at the same time, we see that children learn their native languages in a relatively short span, and they do it with incredibly limited data. Children are only seeing, a very limited swath of what's actually allowed in their language, and yet they all achieve really high competence very uniformly. So like human children are doing some amazing task of learning these complicated rules and patterns very quickly and with not a lot of data. So the big question here is, how are they doing it? How is this possible? And this is something that has occupied linguists for decades. So this is Noam Chomsky. You may be familiar with him from many different areas. He's kind of got his finger in a lot of fields, but he's sort of also known as, in some circles, the father of linguistics. Like he's been working on linguistics for a long time. He's done a lot of very foundational work in the field. And these are the questions that he thinks are of central concern to linguists. So what constitutes knowledge of language? What does it mean to know a language? And then how is this knowledge of language acquired? So that's what we're mostly talking about here today. How are humans, how are children actually learning this linguistic knowledge? And then how is this knowledge of language put to use? So all of these questions kind of get at what's going on in the mind when we know a language. So it's very fundamental to understanding how language is represented in the mind and how it gets there. But answering these questions well and successfully also will give us a lot of avenues towards creating successful language technologies. Since humans do this amazingly complicated task, if we can understand better how we do it, it will also help us in the development of any type of language technology. So these are really, really fundamental questions and things that have been sort of, I guess, as Thomas said, really important to linguists for a long time. But at the same time, there's still very little work that actually offers a systematic theory of language. So this is sort of this big gap in our knowledge as linguists, like how are we doing this amazing feat of learning? So this work is sort of my own like humble attempt to plug that gap and make some kind of progress towards an account of language learning that is formal and interpretable, so that we can make sort of understand deeply and mathematically and make guarantees about it. Okay, so with that, I'll tell you what we're going to talk about today. So we just went over a little bit of the motivation, like why do we care about this? Next, I'm going to dive into some background. We're going to talk about sort of the hypothesis space for learning and how that's going to be the angle that I'm going to come at that from. And then like we'll talk a little bit about tree structure, which is how we understand syntax or sentence structure, and how we're going to represent it. And then I'll talk about the actual learning algorithm that I've been working on. I'm not going to go into like really fine-grained technical detail, but I will try to give sort of a intuition for what it does and how it works. So hopefully at least you can get sort of a feel for it that way. And then I'm going to talk about some particular applications of this algorithm and some simulations using a working prototype that I've invented. And then I'll conclude with why we care about this again. So let's dive into the background here. So when we're talking about learning, right, we're basically talking about something that a process that's going to take some sample of input data, some kind of input data, but that has to be finite, right? Like we can't allow learning to go on forever, at least not for human children or any of our machines either, right? Like we have to have some bound on that. So we have some finite number of things that we're allowed to look at during learning. And then when we're done, we need to output sort of something that represents the knowledge that we've just gained. And in this case, we're going to call it a grammar. And the grammar itself is basically going to be a device that sort of takes a possible expression or sentence that like might or might not be in your language and tells you whether it's in or it's out. So this is a membership problem, right? And like obviously there's other things that go into our knowledge of language other than just membership. But this is a pretty fundamental one. So this is what we're focusing on here. So in a sense, we can think of a learning algorithm as being a function from the input sample to the grammar. And then the grammar itself is sort of a function which solves this decision problem. And it's worth noting that like most human languages, like many languages and certainly all human languages, we consider them to be these like infinite objects, right? So you're only going to hear a finite number of sentences during learning or whatever. But for probably every day, each of us say a sentence that no one has ever said before or had even thought of saying, right? And we can just imagine, doing that forever. So our language has sort of these infinite possible things that we could say, but we're only going to get to see a finite number of them during learning. So we're going to have to kind of learn the shape of this infinite set using this finite set of examples. So in order to do that well, we need a hypothesis space, which is the set of possible grammars that we're sort of willing to entertain, right? So if we remove the idea of hypothesis space and we say, no, we sort of want to be able to learn, any shape of set, we're gonna have a problem because we'll never know when to generalize. So our hypothesis space tells us, okay, when can I take the data that I've seen and how can I generalize that to conclude that there's new data that I haven't seen that's going to be allowed in the language. So we need some kind of concept that defines, okay, these are the possible ways that my grammar could look. And without having that, we can't learn. So what are we gonna use as our hypothesis space for natural language? Well, fortunately for me, lots of people are already working on this. So folks here at Stony Brook and other places have been working on something called subregular linguistics. And basically the idea here is that they're using these formal languages, which are sort of string sets that are mathematically defined and can be categorized according to sort of how complex of a device you need to compute those string sets. So like how complicated of a grammar or what kind of a grammar do you need to solve the decision problem about these string sets. And so there's this sort of rich landscape of these classes or categories of formal languages that folks have been looking into to try to understand, okay, when we look at things in natural language, what kind of machinery would we need to actually compute those things, and like, how do they match up to the different complexities of these formal languages? So the idea here is like to identify formal classes, so mathematically defined sets, which align closely with the behavior we see in natural language. So we want whatever class we're going to use to be able to sort of be expressive enough to account for all the things that we see in natural language, but we also want it to be limited enough that we can still learn it. And that it doesn't do lots of weird things that we don't see in natural language. So once we sort of identify these relevant classes, the next step is to show that they actually can be learned. So that's kind of where this work fits in. I'm working on a particular learning algorithm for a particular one of these classes, which I'll talk a little bit more about in a minute. And then, of course, sort of in the future direction, the idea is to not just show that these things can be learned, but actually adapt and create algorithms so that they show the similar learning behavior to what humans actually show. So this is kind of sort of like the refinement step to try and actually match human behavior. So kind of zooming into on this like huge diagram here with all these classes, we're sort of in this sort of simple space where the formal languages that we care about are less complex than the regular languages, if you're familiar with those. So regular languages are basically languages which can be computed with finite memory bound. And we want to be below that in complexity. So there's a lot of recent work suggesting that that phenomena across linguistic domains, so things like sound structure, sentence structure, word structure, all of them can be captured by a few of these subregular classes. And particularly the classes of strictly local, SL, and tier-based strictly local, TSL. So these guys are really useful for talking about phenomena across linguistic domains. And here I'm going to be talking about a learning algorithm for a related class called MTSL, which is basically like if you have a bunch of TSL things going on at once, you get MTSL. And this will extend an existing result from learning string languages to learning tree languages, which is what we use for syntax or sentence structure, and kind of bring us towards a theory of language learning that is sort of unified across these domains. This kind of a subregular approach allows us to kind of unify the string structure and the tree structure worlds into like one sort of cohesive story. So let's zoom in a little bit on what the TSL languages actually are. So tier-based strictly local languages can be defined by restrictions on local configurations of elements. So configurations of elements that are immediately next to each other once we ignore a given set of irrelevant symbols, right? So over here on the right, this is an example from a language called Samala, and they have this process known as sibilant harmony, where in a word, you can have the letter S that's fine. It can appear as many times as you want. Or you can have the letter, this wiggly guy here is like an SH sound. Ash. So you can have, and we call it an esh. So you can have the SH sound as many times as you want in a word, that's totally fine. But you cannot mix them. So regardless of how many letters are in between the S and the esh, you're not allowed to have them together in the same word, right? So here we can see that to sort of compute this process, what we need to do is essentially ignore all of these letters that aren't sibilants, this S sound and the SH sound. And then we're left with just those sibilant sounds, and we can see, okay, who's next to each other. So the grammaticality of a word for a TSL language must be entirely predictable from the set of k-grams. So that's like, you know, immediately adjacent substrings of letters. And here we're looking at TSL2. So we're just looking at each pair of letters that's next to each other. So we have to be able to fully predict the grammaticality of a word, the legalness of a word, based on the set of pairs of letters that it contains. So this first guy up here, Sapitsolus, right? When we project the tier, when we like sort of get rid of all these other guys that don't matter, what we have left over is, okay, S next to S, and then another one, S next to S, right? So the only sort of bigram that's in that word on that tier is just SS, and that's totally fine, we're allowed to have that. And then similarly here, this is actually the same word, and I believe this suffix wash here is just a past tense marker. So when you slap on that past tense marker, you actually get that all of the sibilants in the whole word are gonna change to match the esh sound at the end, right? So that we don't violate this rule about not mixing them in the word. And when we project that onto our tier, again, we see that all of the bigrams look like esh, esh, another one, esh, esh, right? That's all we have in the word, and that's okay. But if we were to, for example, fail to apply this process and change the other sibilants in the word, right? Suddenly our bigrams, okay, we still have SS here and another one, but now we also have SH here at the end. And that's not allowed, right? And just that one illicit bigram is enough to make that word illegal, right? That's not a word of some law, you're not allowed to use it. You're not allowed to say it. So like this wouldn't be a phonologically illicit word just because of this one bigram. And we can do this for any size of K, like typically in sound structure, we are sticking to small Ks, something like maybe 3 or 4 for most languages. But in principle, you can do it for any K. So again, the idea is basically we care about these substructures that are projected onto this tier where we're sort of getting rid of these irrelevant letters. So in syntax, right, we're not really talking about strings usually. When we talk about sentence structure, we typically want to encode some sort of hierarchical relationships. And so we use these structures called trees, which kind of look basically like this, right? Like we can represent hierarchy where something is sort of sitting above other things that it connects. And so we can use a similar idea here of ignoring certain symbols to produce tree tiers, right? Because we want to kind of be able to say, okay, we have this class of TSL over strings. It works really well for categorizing stuff in phonology, which refers to like sound structure. We want to use it we want to see what happens if we try and use it for syntax. But in syntax, we're working with trees. So we better figure out some way to make some kind of tier on the tree. So we can do a similar thing, right? We can say, okay, suppose we have this tree here on the left, but we only really care about A and B. We don't care about C and D. They're not relevant, right? So we want to project the A-B tier, right? So you can kind of think of this as if you're like going through the tree and every time you find something irrelevant, you like rip it out and you stick its children, like the things underneath it, right back where it came from. So here, if we were to take this tree and project it onto the A-B tier, we get this tree over here on the left. And it's worth noting that when we do something like project this kind of tier, we can go from this is a binary branching tree on the left where every single node is only allowed to have 2 children. But we can get something like this guy on the right where suddenly this B node has 3 children. So some of the properties of the shape of the tree are actually not preserved when we do this sort of like tierification. But this is what a tree tier is going to look like for us. So then we want to be able to say, okay, we can project a tier on the tree, and then similar to TSL over strings, we want to be able to specify sort of like k-size substructures. So in this case, we're looking at particularly TSL2, so substructures of size 2 that we can either say are allowed or not allowed in our language, right? So this is similar to saying like, oh, the SS bigram is banned, right? So these in over trees, we're going to call these two factors, and they consist of pairs of symbols which are immediately local to each other. So they will be like either in the parenthood relation or the siblinghood relation, which basically means like, for example, this guy, like A and B are immediately local, right? A is immediately above B, and we would say A is the parent of B here, right? And then like similarly, we can go through and find like all of the different two factors in this tree. So here A is the parent of C, here C is the parent of B, and C is the parent of A. And then similarly, we can look at the siblinghood relation, which just encodes which guys are immediately adjacent and share a parent, right? So they have to be immediately adjacent children of the same parent. So like here, we have B and C in a siblinghood relation and B and A in a siblinghood relation. And we're preserving the order here. We're noticing like, okay, B is the immediate left sibling of C, and here it's the immediately left sibling of A. So these are tree two factors. So then when we look at tree TSL, the things that we're going to be banning, like the things that are going to be not allowed on our tiers, are going to be this kind of thing. So these parenthood relations and these siblinghood relations that are pairs of elements. Okay, so the next thing that we have to do is we have to basically have a way to actually represent our sentences. So we're going to be using this thing called dependency trees. And basically, what this is doing is kind of encoding the meaning relationships between words, right? So in this case, right, like a verb like said kind of introduces two different arguments or things into the discussion, right? You need someone to have done the saying, and you need something that they said, right? So in this case, like you is the subject here, introduced by said, and then the thing that was said is kind of this whole clause. And then similarly, like the word that, right, is introducing a new clause that we're about to start, right? So it's going to be the parent of this clause. And then, saw here is another verb that introduces two things. In this case, it's usually, some kind of noun doing the seeing and then some kind of noun that was seen, right? So here it's introducing Mary as the subject of saw and John as the object. And when we linearize this, we just get, you said that Mary saw John, right?
Logan?
Yeah.
Sorry, just a detail. You just said that this encodes semantic information, but it actually is syntactic information, right? I mean, subjecthood is a syntactic notion. And
yeah, so
it's as close to semantics as you sort of get in the syntactic world, but it is syntax.
It is syntax. Yeah, so I guess if you're not familiar with syntax, you can think of this like encoding some kind of meaning relation, but it is basically like Owen said, as close as you can get to that kind of meaning relationship, but still be syntax fundamentally. Yeah. So there is like there's a structural relationship going on here. So I see a lot of linguists in the room. So, if you're familiar with that, this probably looks a little different than the syntax trees that you're used to. But it is still, syntax here. And we can actually go back and forth kind of nicely from this to like the things that you might be more used to. If you're not a linguist, just ignore all of that. This represents basically the meanings and how they're connected. Yeah. So then we also need a way to sort of handle this kind of thing where like we have something that looks like it moved around in our sentence, right? So if we turn you said that Mary saw John into a question and we want to ask about like who is being seen, right? The thing that was being seen no longer lives at the end of the sentence here. It comes up here and is it now here at the beginning, right? So we want to encode that on our tree here. We're going to use this little notation that's sort of we're going to call it a feature. This little guy here that basically says, okay, I'm the word who, that's what this means, but then also like, I'm going to move, right? Like I'm going to go somewhere. And then we sort of encode like where it's going to move to with this like WH plus feature. And this says, like, I'm going to attract a WH word. Something WH like is going to come to where I am. And then these guys kind of have to match up. So the WH plus attracts the WH minus. And when we actually linearize this into a sentence, the who, which is like sort of the part that actually is said out loud, is going to be realized up here. We're actually going to say it at the beginning of the sentence, up by did, right? Rather than down here at the end. So this is the basics of how we encode movement in this system. And there's sort of a few complexities that are getting skipped over here, but this is kind of the basic idea for how we're going to represent the sentence structure that we want to learn.
I have.
Yeah.
So is the order matter?
Yes, it does matter for this tree. So here, like the first guy here on the left is going to be the thing doing the seeing, or the subject of saw, and the guy on the right is going to be the object of saw, and it's also going to be relevant for the order that we linearize it in. So we would say Mary saw John. This tree is not equivalent to, like, if you switch them, John saw Mary. Yeah, so it does. So yeah, in certain kinds of syntax, you might want to say it doesn't matter, but for right now, yes, it does matter in this
So when you're looking off of it, the order of the word.
Yes, absolutely. So you have to know, like, this is the first child and this is the second child, and not just that they're both children. There's an order to the child relation. Yeah, good question. Thank you. Yeah.
There's no order with respect to the head. Just the children are ordered, but they're not ordered with respect to the head. I mean, how is saw in that order? They're exactly in the same position.
Oh,
Sorry.
they're not, I mean, the saw is just the first child of that.
It's first child.
So like they're in a parent dominance relationship, not a sibling relationship. So yeah. I guess they're just two different types of order, right? So you have parenthood, that's defining one kind of order, one kind of relation, and then siblinghood, right? So and that's kind of the two factors that we saw. Yeah, Abed.
But are you having the tag subject object already include the order?
Can you say again louder?
Would
Sorry.
it including the subject object tags or whatever we call the labels, which is already include the order in the tree?
Yeah, okay, so we have this subject feature here, and this is actually kind of standing in for like EPP movement for the linguist. So like, yeah, there's this tag here that's telling us it's the subject. But really this is having to do with a different type of movement that we have in English, where we say that the subject of a sentence undergoes this other movement, and this is sort of hiding that, basically. Yeah. So we're not necessarily directly encoding who's the subject. So, yeah, good questions. Thank you guys. Okay, so this is how our trees are going to look. So let's take a look at like how one of these TSL analyses might play out. So here we are with our licit sentence, this sentence that's okay on the left, where we can say, who did you say that Mary saw? And this illegal sentence on the right, who did you say that saw John? That's pretty bad for me. So the things that we care about in this case are really only the that node, right? We need to know whether or not there's a that in our sentence, because without a that, this is okay. And then we care about these like WHE guys, the places they're moving to and the places they're moving from, right? Because typically this constraint is sort of stated as like, okay, you can't have a that immediately followed by this place where there used to be something that moved away, right? So this sort of like underscore is indicating there was something here, this like WH element, where it would naturally live if this wasn't a question, and it's gone. So we're not really supposed to have like that followed by something that used to be there, and then, right? So, okay, here's our trees for those two sentences. This is kind of like what we just looked at. There's WH mover over here. The subject is the WH mover, right? So if we project just these relevant guys onto a tier, these trees suddenly become like really simple and basic. So these are still trees, but they're just like one parent, one child, one parent, one child. So this kind of linear looking, but vertical arrangement, right? So we have the WH landing sites, we have the WH movers, and we have the that element. So once we've gotten it down to these like tiers that only have these relevant things on them, suddenly it's immediately like, it's very simple to say which one of these is good and bad. Like it immediately jumps out what the difference between these is, right? And that's that on the right, we have our that element immediately being the immediate parent of this guy who's gonna move, right? But who's also the subject, right? So that means it's gonna come directly after the that, right? And also then move, right? So here's that gap where it would show up. So we can say, okay, boom, that's the thing we want to ban, right? That's not allowed. So this slash is just indicating parenthood. So we can't have a that directly over a subject who's also a WH, right? And so suddenly this like weird, complicated, strange pattern is like pretty simple to, if not simple to understand why it's there, it's very simple to understand sort of how to rule stuff out that you wanna rule out. Yeah. The plus and minus, it's not so important for what we're talking about, but basically it's indicating the plus is like, I want a WH thing, like I'm attracting one, and the minus is saying I am a WH thing. WH word being like any question word, like who, what, whatever. So it's just indicating, movement. It's indicating like when you have a little minus feature, it's saying I'm gonna move somewhere and I'm looking for something that matches that to move to, that has a plus. So that's how we get this sort of like where Mary would have been, right? Mary saw John. There's nothing, but at the beginning of the sentence, it's true, right? And so like we kind of would say, all right, maybe that who basically moved from that subject position of the embedded clause all the way to the beginning of the sentence. And this little feature here is that's what's telling us. When you pronounce this sentence, don't pronounce the who down here. And don't say, did you say that who saw John? Pronounce it up here at the beginning and say, who did you say that saw John? Does that make sense?
So basically like the second H, WH is kind of responding to the subject.
Yes, so this guy here is both a WH mover and the subject, yeah. The thing that's doing the seeing, and that's what we're extracting, creating this sentence that is not so good. Doesn't sound good to an English speaker. Yeah. And that's the crucial difference here is that this who on the right that we're moving is the subject, whereas this one, not the subject, we don't care, it's okay. Does it make sense? Okay, yeah, so these little guys are just telling us where we're gonna move stuff, right? But it's crucial to know for this sort of tier analysis because we only care about something if it's gonna be a mover, right? So we only are gonna put it on our tier if it has that WH feature on it.
Why the second one doesn't work?
So this one is the one that corresponds to who did you say that saw John? And so it may be that this actually sounds totally fine to you, I don't know. Some native English speakers will say, no, it's fine. For me, it's very bad, right? So the pattern that we're seeing is that like typically for people who have whatever my dialect is, you can't have a that sort of thing that introduces a new clause and then immediately have this empty subject position. That doesn't sound right to me. Okay. But if you're in a dialect where that isn't true, you just say, oh no, that's not a constraint, right? It's just a different language, that constraint is missing, right? So that's just what's allowing us to pick out, okay, this one on the right, that's the crucial difference that's making it sound bad. Okay, so that's tree TSL. And so any given language is not just gonna have like one, thing going on in the syntax at a given time, right? There's like a bunch of different processes and phenomena that we care about in the syntax. So a bunch of like different potentially complicated patterns. So like we've seen, there's a lot of work saying that like almost all of them are actually, they look like this. They're analyzable as a TSL2 tree pattern. So a multi-tier-based strictly local, whatever, MTSL, tree language is basically just a language where there's several different TSL things going on at once. So the intersection of multiple TSL2 languages. And so I'm about to present a learning algorithm which learns the class of learns this close approximation of the class of MTSL2 from a bounded input sample of well-formed trees. And yeah, Owen?
So what is a tree language?
So a tree language is similar to how we might say a formal language over strings is a string set. A tree language is just a set of trees.
So you define a set of constraints on the paths and trees, and any tree that matches that is in the tree language.
Yes,
Is that
exactly.
right?
So your grammar looks like a bunch of constraints, and it can then look at a tree and say, this follows my constraints, or no, it doesn't follow my constraints. And if it violates a constraint, it's not in the language, otherwise it's in the language. So it just forms a set.
And you can formulate constraints, as you said earlier, over dominance relations and over sibling relations.
Yes.
And this is marked to the constraints, what it applies.
Yes, and so each constraint in like MTSL it'll be the symbols in the constraint, it'll be the relationship that they stand in, and it will be the tier that is relevant, right? So like if it's this one, the tier is just that and WH, right? And because it's multi-tier-based strictly local, you might have many different tiers going on. So different constraints might be blocked on different tiers.
And can you mix and match dominance and sibling in a constraint formulation?
Not in a single constraint because it's MTSL2, but you can have one tier that has multiple constraints that do different things. But a single constraint is only talking about two elements. So they're either going to be sibling or dominance. Those are the only types of relationships we can talk about.
Thank you.
Yeah, okay, so the algorithm I'm going to present here, I'm not going to go into either the proof or the sort of technical parts of the algorithm, but you just have to take my word for it, or you can read the paper, that it will efficiently learn this class from a bounded input of well-formed trees, meaning it's only learning from positive data. Yeah. Okay, so we're going to dive into the learning algorithm now, and I'll try and just give sort of a felt sense for like how it operates as opposed to sort of a extremely technical walkthrough. So this algorithm is called the multi-tier-based strictly local inference algorithm. Try saying that 5 times fast. But we've got this handy abbreviation, MT2SLIA. And this builds on work on learning MTSL2 over strings and sort of adapts it and lifts it to tree languages. So this is a batch learner. All the data sort of comes in up front. And the idea here is that we're going to leverage the idea that anything, so any of these two factors, either dominance or siblinghood, which is missing in our input sample, is missing for a principled reason. And that reason is there's some constraint against that particular substructure. And the idea is, okay, we want to construct the most restrictive tier. So like, I guess, so actually the most restrictive tier is going to be the smallest tier, which will ban the constraint in the most places, right? So the idea is look for things that are missing, and we're going to assume those are missing for a principled reason, and then we're going to try and say, okay, what is the correct tier that constraint should live on? So yeah, so this algorithm proceeds totally unsupervised, right? It just gets the data and it does its thing. There's not like feedback about its predictions. And it's only learning from positive data. So, right, so it gets all this positive data, it does its thing, it spits out a grammar. There isn't some kind of feedback loop where it can like ask, am I right about this? Or is it getting some kind of feedback, which is how we generally think that children actually learn, right? Like primarily hear positive data. And if they do get some kind of feedback on like whether or not they're doing it right, the evidence suggests they actually largely totally ignore it, right? Like if their parents say, oh no, say it this way, the child will like completely ignore it. So this is this learning paradigm is meant to kind of be a good proxy for like what children may be experiencing. So we're gonna just do a pretty quick high level of like what's going on in this algorithm, rather than getting really into the details. So if you don't fully understand exactly everything that's happening here, it's okay, don't worry about it. We can talk about it later, or there's like, you know, I have a paper on this that kind of goes into the actual like deep math of it. But basically the idea, right, is that we're looking for things that are missing in our data. So what substructures of size 2 are absent? So if we're given this sample of trees, right, it doesn't really look, you know, to a quick glance like there's like some kind of clear pattern going on here. But what the algorithm is going to do is it's going to say, okay, what substructures are missing? And it turns out that all the configurations of A's, B's, and C's that you can imagine are present in this data except for this C being the parent of B, right? Like all the C's, none of them have a B child. And then B being a left sibling of A, and C being a left sibling of B. So these are the only three missing substructures, right? So then the algorithm is going to say, okay, if those are missing, they're missing for a reason. I want to figure out which tier they're banned on. So like for C dominating B, it actually turns out that not only does C is never the immediate parent of B, but actually there's no tier that you can project where you'll get a C being a parent of B. And that's pretty easy to ascertain, because you can just look and see that like all of these C nodes, the only thing that's ever coming underneath them is an A. So no matter what tier you project, you're never going to get C as a parent and B as a child. So in that case, we're just going to say, okay, the tier is just C and B, right? There's no reason to project A because that's not changing whether or not it's present. Meanwhile, for something like B as a left sibling of A, we can see that, okay, actually it turns out if we rip this C node out of this tree and just projected the A-B tier here, we actually would get B as a left sibling of A. So we can't say, oh, the tier is only A and B, right? We have to say, okay, C is on the tier, because it's doing this like interference effect, where when C is interfering between B and A being siblings, suddenly that's allowed, right? So it must be on the tier. And you can do a similar thing with the C and B as siblings of each other. I'm not going to go through it, but you can check. It involves ripping out this A node here, basically. So this is kind of how the algorithm proceeds. And I guess I'll just have to take my word for it for now that this approach correctly learns the class that I say it does, because what I really want to do is talk about, and I only have a few minutes, I really want to talk about some of the applications. So I have actually constructed a working prototype of this algorithm, and I'm using it to try and test out its behavior on a few actual natural language patterns. So that the way that this works is basically you give it these JSON formatted dependency trees. So these look a little more complicated than what we were just looking at, but they're encoding the same information, the same kind of ideas that we were just seeing. And then it's going to output a list of constraints and the tiers that they're sort of associated to. So the constraints, the tiers will look like this, like the elements that are banned, and then the constraints look like this. They're a little hard to read just because of the ASCII kind of symbol, but I'll talk you through it. So I've run a couple of preliminary simulations on a couple different phenomena that I'll talk about. And these are sort of small hand curated training and test sets. So this is an example of one on the right. So they're very small. They only have a few examples. And the idea is to like target a really particular phenomenon for which we actually know what the pattern is. So we know what it's trying to learn. And this is kind of, I'm trying to have this careful, controlled way to give a proof of concept about what it can do and show that it can learn these particular things, kind of before just diving into like a huge corpus where you don't necessarily know what all the restrictions that the patterns that it should find actually even are. Yeah, and so because of this, right, we have this like small data, and it's worth noting that like we're gonna get lots of constraints that like may not correspond to the pattern that we're looking at. And that is expected, right? Because the whole idea is here, we're doing MTSL, right? So it's trying to look for like all the patterns that are present at once. And because this is natural language data, there are many patterns present at once. But we're sort of zeroing in on like whatever one, we're looking at. So this is a simulation I did with that trace effect. And the input sample is just this, it's just these 6 sentences here. And you can see they're all well formed according to this rule. So we never have this that followed by an extracted subject that would be the banned stuff. So these well-formed sentences, there's a few without WH, there's one without WH movement. We have WH movement here. And then we have like this sort of like embedded clause here, like who do you believe Dave said Mary saw? So we can sort of do this like nesting thing. And this is where you can kind of see like these sentences could get infinitely wrong, right? Like who do you believe that Dave said that Mary reported that Peter thinks that whatever. saw John or whatever. So like you can kind of imagine extending these forever, and we want our grammar to still be able to make the correct distinction that we want between what's grammatical and what's ungrammatical, right? So I ran it on this six sentences, and I got out grammar containing 43 constraints, which I haven't put all of them here because it would just give everyone a headache. I see, let's see. So the crucial one is right here. So this is the constraint saying you can't have a that's a parent of WH mover and also a subject. The subject feature has magically transformed to this nominative nom thing here. But just take my word for it. This is the WH mover subject, and this is the that node, right? You're not allowed to have that dominating this guy. And it's projected this tier with these like certain things on it. This is roughly what we had, although this looks a little different, but I won't get into why that is. So we can see that actually, so I put together this test data set, also very small. And it's got this one grammatical sentence that was unseen in the training data. Who do you believe Dave said that Mary saw? And it's able to say, yep, that sentence is fine. But it's also able to say this sentence, which it certainly never saw because it only trains on positive data. It's able to say this sentence, who did you say that saw John? That's bad, that's no good. So it rules that out. And it also rules out this longer sentence, who do you believe that Dave said that saw John? Also out for the same exact reason. And it's this constraint that's doing that ruling. And then I just put one of the other constraints here just to show that like these other constraints like are trying to get at some of the other patterns in language. This constraint here is essentially saying a clause cannot have two subjects, right? The constraint is saying subject is a sibling of another subject, and the tier includes these C's are like the clause boundary. So a clause can't have two subjects in it, right? So then there's all these other constraints, right, that are like trying to get at these other things. So in a sense, it's sort of like overfitted, but the point here is that it can correctly both allow this guy that should be allowed and ban these guys. So it's able to sort of zero in on this phenomenon. And I think for the sake of time, I'm gonna skip, much as I want to talk about it, the WH copying example. This is another simulation that I ran. It requires explaining this particular pattern in German, which I just don't think we have time to do. If you want to ask me about it after, feel free. But I have run another simulation on another natural language pattern. And again, it's TSL, hooray. Again, I was able to get the exact correct predictions with this one constraint that's doing, or this set of constraints that are doing the heavy lifting to correctly sort these according to how linguists already know this pattern works. So for the sake of time, moving on from that, let's just conclude here because I want to have at least a couple minutes for people to ask questions in case I like totally bamboozled everyone. So just to recap, today I talked about my algorithm, the MT2SLIA. This algorithm provably learns the class of MTSL star. And it's unsupervised. It learns in an efficient amount of time and data complexity from only positive examples. I've tested this algorithm on multiple phenomena from natural language, yielding promising results about its ability to like correctly learn these phenomena. We talked about the that trace effect. We didn't talk about German WH copying. In the future, I really want to turn this into a more scalable implementation. And what I really want to do is create data sets that are modular but can be combined, right? We have MTSL here, multi-tier-based. I want to be able to say, okay, let me pick out these 3 different phenomena and try and learn them all at once and see what happens, or learn how they interact. So I want to like keep building the data sets that I have. Right now, everything I have is like painstakingly curated by me personally. I would love to sort of like ideally eventually move to like a tree bank or larger corpus. It will probably require some formatting work and stuff to sort of deal with the way that syntactic corpora look. But yeah, ideally, the next steps mostly involve scaling this. And then just to conclude, the learnability guarantees that are given by this algorithm, as well as the results that I just talked about and sort of skipped over slightly from the early testing, I believe make this class of languages a viable candidate to represent the space of possible human languages. And this learning algorithm, it works over trees, as I just showed, but it's also a relevant algorithm for learning things in sound structure, like phonology and morphology, which are like sound structure and word structure, which look like strings, right? So this is sort of a huge step towards unifying a theory of language learning, which applies in syntax, but also applies in phonology and can kind of like cut across the different domains of linguistics to sort of have a single cohesive story about how learning happens, for which we have like a deep understanding of how it works. And that's what I have to say. These are my references. Thank you.
Okay, thanks for the talk. I haven't really thought much about learning, but one thing that this is not a question about in the scope of this, and I think it's like not in the scope of like future steps, but so the algorithm takes like trees as input, right? But I was just wondering, like humans don't, right? Like we have string.
Yes.
So this sort of learning and the learning, I guess I was just wondering what your opinion is on like how much of the structure is like, I don't know, universal grammar, whatever. How much of it is just like learned sort of at the same time, right?
Yeah, so this is a question I actually do take very seriously. And I guess if I had like future directions and then like future directions, it would go in there. Because I do like, obviously we're starting from trees, but no child is like hearing a tree coming into their brain. So I guess the first thing I would say is that working with dependency trees, I'm like, okay, this is nice because you're a little closer to like the meanings of things. So getting from a sentence to how the tree might look, I would argue is a bit less of a complicated problem than it would be if like, if you use a different format of tree. And we can still encode like the same stuff we want to encode. So there's that, but then I guess I also would say like looking at, learning the trees is definitely like in the realm of like what I would like to look at. And I don't wanna brush under the rug like that idea. I do think it's very relevant that what we hear is actually in linear time, a sort of string of sounds. So yeah, future directions, I guess.
I was just wondering how much of like this data that we learn based on is actually very noisy because of all of the wrong trees that we're assuming at some point.
Yeah, that's interesting. And also noisy because people make mistakes and stuff, right? Yeah, I don't know. I mean, I guess my feeling would be to say most of that is learned and like not in UG somewhere. But I don't know. People can certainly argue with me about that.
Definitely all the stuff that's different in different languages.
Right, yeah. Yeah, thank you. Yeah.
So I saw that we have like 43 constraints.
Mhm.
How many of these are actually needed to? Is every constraint as important as one, or is there like a distribution where one constraint?
Yeah, so this is the thing, right, about learning like one particular little phenomenon. So like the constraint that actually enforces that trace effect is one constraint.
Right.
Just one out of those 43, which is what I, the researcher, am looking at whether or not it can get. I guess it's hard for me to say like it's hard to start saying what are important and not important constraints, because to some extent, I mean, the thing about the constraints is that they're just all true, right? So the algorithm is just telling you all the constraints that are true on the data within its concept class, its hypothesis space of things it's allowed to posit, right? So if you're looking at more data and like many things going on at once, you might see constraints in there that as a syntactician or a linguist, you're like, I have no idea what this is. It doesn't seem very important, right? But the algorithm is just telling you this is true. And maybe it would actually lead you to find something that you wouldn't have looked for before, but actually does seem to be a consistent, generalization for speakers. At the same time, maybe you find something and you're like, I think this is just, like the other option is it's just kind of overtrained, right? It's like overfitted to the data. So I guess it's hard to answer which ones are more important. Certainly only some of them are actually, only very few of them are actually doing the thing that I'm looking at, particularly in any given example. But all of them are true, right? And we have this small data sample, so a ton of constraints are true because there's a ton of stuff that's not in there. Bigger samples will have less of that, basically. Yeah.
So your algorithm is efficient But like when you increase a set, so the number of like your lexicon for your tree, the number of subsets and even the subsets of size 2 that you can get out of that. So the number of tiers, right? That increases like incredibly quickly.
Yes,
So how do you get around that?
that's a really great question. So I guess at some point I said something like I'm learning a close approximation or like close, MTSL star. This is one of the places where that comes in. So the concept class that's actually being learned has this restriction that no single constraint can show up on two different tiers which are incomparable. So it gets around it because the search is bounded by the constraints rather than the tiers, if that answers your question.
Yeah, I guess.
We're not searching over every single tier because we're looking at each constraint and saying which tier does that constraint belong on.
Oh, I
It
see.
only belongs on one tier.
Oh, I see.
Thus, we don't have to search all the tiers because we're only gonna get as many tiers as we have constraints, right? But you're right, the tier space blows up exponentially. So if you were actually looking at every single tier, you'd be in trouble from an efficiency perspective. Yes. I think there's a question here.
So I'm not very expertise in linguistics.
Can you speak louder, please? Thank you.
Yeah, I'm just wondering what is the real meaning of learning here, because from my expertise, like learning is used for like machine learning, computer learning, whatever. So is learning corresponding to that learning, or is it a little bit?
Yeah, okay, that's a very deep question. If anyone didn't hear, the question was like, what is the meaning of learning in this context? Basically, I think. So I guess here, right, the meaning of learning is, we're talking about this like sort of formal mathematical thing. And so in this case, as I've defined this algorithm, the meaning of learning is exact identification of the target class, the target grammar, within these restrictions on time and efficiency, right? So usually in like the ML literature or something, whether or not you've learned something is typically measured by like how well you do on your test set or something, right? And like I showed these test sets here, but this algorithm has mathematically provable results where if it gets a certain sample, a certain well-defined sample of input, it's guaranteed to exactly identify the target output class, right? So here, the meaning of learning that I'm using is this particular definition that says exact identification in polynomial time and polynomial data. Maybe that's too technical, but basically I'm identifying exactly the correct class, and by that I mean we're creating this grammar that is solving the membership problem, right? So the grammar that is output is guaranteed if it sees the appropriate input sample. The grammar that is output is guaranteed to produce accurate results on every single member of that, like every single sentence will be correctly identified as in the language or out of the language if the algorithm gets the complete sample. So there won't be like, precision, blah, 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 recall, whatever. If you get the sample, you learn the target. That's the mathematical guarantee.
So if I remember correct, if I understood it correctly, that means you have the hypothesis of the tree structure and you have the data set, well-defined data set, and then you wanted to see what kind of like the grammar which is not designated in the tree structure when you've got from as an output.
Yeah, pretty much exactly. Yeah. Yeah. So you have an idea of like what your possible grammars are allowed to look like. You have some data and the algorithm gets you from data to one of those possible grammars, which should be the target one. Yeah.
So for that, like we have the characters like from A to B, and then you want to find
Yeah, so the grammar is going to look like these siblinghood or parenthood relationships, right? And then corresponding tiers where they are forbidden, basically. Yeah. Yeah, I think you basically yeah.
I just want to say real quick, like, one, we also have like a brown bag starting in the linguistics department right now, so if somebody wants to go there now, that's A-OK.
Hey, you're free to leave. Yeah, I'm not holding anyone hostage.
So my question is like something, someone who doesn't understand much of this at all. How is this affected by meaning? Meaning the sentences have meaning, right? It rather conveys some information. This doesn't look like it's connected to transmitting any information, it's about a pattern encoded in the language.
Yeah, so this is sort of when we talk about what it means to know a language, right? There's several pieces to that, right? And one of those pieces is like, how do you get meaning from a sentence, and then how do you take a meaning and turn it into a sentence, right? This is more about the structure of a language. So like, what kinds of structures are you allowed to build, sort of independent of meaning? So like, I don't know, linguists like to talk about the sentence, colorless green ideas sing furiously, right? It means nothing, but we know that it's allowed, right? So this is solving that membership problem, right? It's saying what's actually allowed in the language without touching on this component of like, how do you infuse the meaning in either direction, basically. So that's just sort of a different piece of what linguistic knowledge means, and it's certainly not one that is inconsequential, but it's sort of out of scope for this.
Would you take it faster? That's what I was wondering. Or like, to learn or see or something, if it had.
Well, I guess I would say that like learning, like to put to us to see this question about like, how do you get an actual tree from the sentence that you hear, that you're hearing in linear, linear in time, right? I would say using the meaning is really useful to building that tree, right? You're like, okay, I know see is a verb and it needs 2 arguments. Okay, you've started to build up how your tree is gonna look based on knowing what the verb see means, right? So that's where the meaning like comes into this. I think beyond that, I'm not really sure, like, yeah.
Thanks.
It's actually made me think about the fact that people are just not also that good at solving the membership problems. It's like if you ever had to give a grammatic analysis, it's not actually that.
Depending on the phenomenon.
Speak English to an Indian English speaker. And I asked to explain how prepone meeting exists.
Yeah, I don't.
Right, I have to, this is like kind of an annoying question, but I have to ask it. So you're talking about like scaling up to using like maybe like a penny tree bank or something,
Yeah.
right? It seems to me that there are probably errors somewhere in the pen tree bank.
Yes.
Do you know how sensitive this is to it? Do you have any ideas like what you're gonna do to kind of like?
Yeah, so this is pretty noise sensitive, right? Because it's so, the learning paradigm is like exact identification, and it's like not taking any kind of frequency into account or anything. So to move to a corpus, it's like either be really careful with your corpus, maybe is one approach. The other approach is like then actually start getting some noise sensitivity in here. I wouldn't say either, like both of those seem like fine avenues to me, but that's why it's like future. So
I'm curious, like,
totally fair point. This is very noise sensitive. Yeah.
But I mean, your obvious starting point wouldn't be the pen tree bank, it would be the MG
Yeah.
auto bank,
Yeah.
which is a fragment of the pen tree bank and is curated.
so it's very high quality. So
Should
like, we
be,
wouldn't
like, should be pretty much,
Okay.
to the extent where like John Tor, who developed that tree bank, even came up with new MG analyses to account for certain things that aren't in.
Oh,
So it should be pretty.
So it should be a-
good quality.
large. Yes.
Oh, it's small,
How many-
I think like a couple thousand or something.
couple thousand.
That's pretty good for me.
Yeah.
But it's
Like,
better than
compared to the
six,
tree bank,
so.
there's-
Yeah.
But yeah, that would be the obvious start.
Yeah.
All right. Thank you, Logan.